My name is Santanu Das, and currently I'm actually working for Verizon's lab in Palo Alto. Uh, my major emphasis at work is the implementation of machine learning, data mining algorithms, feature extraction techniques, and more, for particularly geared towards large scale system. And today's talk, what I wanted to mention in the keynote is like some of the highlights I have experienced while I went through this journey. Because initially I started as a researcher as NASA Ames, have been involved in PHM field a lot, have been doing a lot of research. In Verizon, the direction changed a bit. Now the challenge is how we can bring some of these interesting algorithm in real application and solve it and get to production. So I will actually try to bring up some of the lesson learned and some of the key things I particularly found very interesting that we should keep in mind as a researcher while we try to design the algorithms, while we try to implement it on use cases, and try to focus more on how we can actually scale the application for different other use cases. So what it means is when we build certain algorithms, it's not only geared or tuned towards a particular use case, but we should be able to scale it for a variety of use cases. That's the kind of the essence of this talk. Uh, I have a few assumptions here that, like the first thing I know, like most of you or all of you are well versed with a lot of these techniques. I have been attending a few talks this morning on deep learning, but my demonstration will be on simple techniques which effectively work on certain use cases and the kind of complexity we see once we try to bring those algorithms in practice, in solving real world problems and put it to production, and how do we manage it. So that's the essence of this talk. First things first, I would like to acknowledge the contributors. They have been like very effective, and they are like excellent data scientists and engineers, and they have actually come up with a concept which I will demonstrate in this talk today. So first I will start with a very simple use case, because as experts in this field, we understand use case, we understand data, and I think that's the correct entry point as my understanding. So I will start with one use case which is more like a cybersecurity use case we have been solving at Verizon's lab. So let's look at the data set, very high level summary of this data. So we had two different kinds of data set here. One is aggregation level. What it means is in the router level, where all the connections were source A connecting to destination B, and the kind of the transaction happening, all this data actually goes through different sets of routers and interfaces, and kind of very high level aggregated data is being obtained there. That's the first data set you see there. That's kind of like sampled every 5 minutes, and we consider it some data set which is in tolerance, not that high volume, because the granularity has been changed, as compared to the data set you see on the lower, like the box below, which we call net flow data. That's actually very highly granular data set. What it means is 1/3 of the US population, when communicating with each other or actually visiting servers and everything. So think about it as from the graph standpoint, like source A connecting to destination B and doing some transaction. So all these IP level information is available in that data. So we don't have to worry, the phone numbers have been hashed and all this stuff, so all those precautions have been taken. So given that, we have like tons of data coming in there, so we'll get different kinds of features from each of these data sets, and we'll move on to the next slide, where we are trying to solve a very small problem, and most likely people who are already aware of some of the security use cases will know that the DDoS problem is kind of a well-known problem. People have come up with a lot of solutions. People have actually investigated throughout. There are many existing solutions, enterprise level or corporate level or even device level solutions exist. Now, the purpose of in this particular talk, I use this particular use case to make sure that the use case itself is simple, and we kind of see the complexity it involves even with a simple use case given the data set. So that's the whole purpose of this. So I'm just making a context here. So now jumping to the algorithm part, I'm sure like everyone in this crowd is well versed of this. Like, so we'll get the data, we'll extract some features, which is the first item. In this case, we extracted actually time embedded features. Next, we applied a k-nearest neighborhood based approach. I think we can have a separate discussion on why we chose that and how we actually plan to solve it. But given that, let's assume that k-nearest neighborhood is one of the techniques, right, for solving this. Then we kind of get to an estimator problem. So in this case, we use the kernel density estimator and finally a detector, which is basically an anomaly detection. So my request to the crowd is to think of this problem very abstract. Think of it as detection problem, as prediction problem. That's where the flavor would be much more clearer here. So so which approach, which technique does matter for sure, but if we keep it abstract, saying we are solving an anomaly detection, that's where we will try to connect some of your use cases. You might be able to connect, we'll connect our use cases, and then we'll demonstrate what it takes. So it's a little kind of faded here, but this is something we came up with. Let's say we get the router data and then we actually run these algorithms. We kind of do the estimation, anomaly detection, and this is kind of a very simple visualization with the possibility of the feedback. This is a demo version which I'm showing you here. So we find anomalies and so forth. Now the point is, once we get to the next level of granularity where we are saying let's focus on the much higher granular data set, which is the IP level data. This is one interface where we produced, where we are trying to identify that out of like millions of IPs, right? So basically these are some of the malicious IP. Again, this is an anomaly detection, outlier detection problem. So let's think of it that way. Now, the part which I really want to focus is when we are designing these algorithms, we'll have to keep in mind, right? So basically, what is the problem exactly am I solving? How is my data set, right? And based on that, if you come to that assumption, that hypothesis, it will help you to choose a lot of data structure issue. For example, are we solving many small problems, or are we solving a single problem which is big, right? Those kind of considerations, once we make, we start digging down into more granular assumptions about how we are going to implement it. Now, question is, if the data grows, then most likely it will not be computed locally. You'll have to distribute it. So once you distribute it, you'll have to start thinking, how is the load balance? So am I distributing the load evenly or not, right? Because that can actually skew the whole thing, and we can get into issues where lot of shuffle issues will come, and things that might run locally faster might take much longer time in a distributed fashion, which is kind of funny, but that comes from the overhead itself. Now, all these things, I'm sure like most of you are well aware, and you actually go through all these considerations, make these assumptions about like how we actually should implement our algorithm in some stage, right? Now, my claim is there are so much more beyond this, because algorithm is actually, machine learning algorithm or some sort of detector or a predictor is a small part of the whole flow. That's the part which I'm trying to emphasize here, and that's the reason I named it. Like, there are much more we need to focus on even when we are designing the algorithm. This is what I already told you. Like, once we can run it locally, there are no issues. You can create that plot pretty simple, and you can come up with some solution within kind of a a week or so. Now the question is, if the data is something which resides on 50 different distribution centers, how are we going to do that? Now the first thing comes to our mind is we need a big cluster for sure. Yeah. So this is a typical example of the cluster we have in Verizon. This is a production cluster which is kind of robust and can take like a reasonable load, have nodes and executors and with memory, right? So while I go through this talk, one more assumption I just want to make sure I convey is I'll be talking about some distributed framework here. Like for example, in particular, like uh, Spark has been popular more recently, which has MLlib, where we find most of the distributed version of the algorithms we use on daily basis. So it will be focused on that part a little bit. So that's one hard assumption here. So let's say we do that, then you might say, okay, is that enough with the cluster? The answer is probably no. We need all these technologies. We need to know what is the kind of distributed framework I'm going to use here. Let's say MLlib we are going to use. We are going to use Spark and something related with Spark, right? Now, let's look at the flow. The kind of use case I showed you in the previous slide, the flow can get pretty complicated, because this is the part to understand. Because let's say in production, when the data ingests and then when the data flows in, then while we are actually addressing those two use cases, now there are so many considerations. We'll have to do different kind of module in the flow itself. For example, we'll have to make streams for 1 minute. We'll have to make streams for 5 minutes because we have two different use cases. Now the whole thing gets so complicated. So what it means is, just having a cluster will not be able to run the entire flow, even though we have the algorithm and we know what to expect, right? So that's the kind of complexity I'm talking about, even with the simplest KNN algorithm most likely we learned on the first lesson, right? So now we have the same cluster, Orion cluster, with all the technologies here. We have Spark, we have Solar, HDFS, in everything like H-base given. Now, this is what was kind of a lesson learned from my end, was like, once we have these technologies, right, what we started doing is we started kind of we had one use case, so we started building the pipeline using all these technologies and to serve a particular kind of use case, let's say. Now the second one came into picture. Second use case came, and now we started redoing it again because the first one was so customized for the earlier use case. That's where we started thinking that, well, let's say when we are kind of addressing the use case, we have kind of very high level abstraction is like the data storage layer, we have the access layer. All these have multiple technologies involved in it, many assumptions, many use case driven kind of technologies here, right? We have the batch mode. What it means is the one we are mostly familiar with, that we read the data and then like the entire data, and then we kind of do the processing. But then there are use cases where the stream is kind of useful, because like particularly for transactional data or for security use cases, the stream data set, maintaining the stream is kind of a key. So now we have algorithms there, and then on the right hand side you see we are trying to add different use cases here, and it will grow for sure, right? So given that, now we feel that we need something to manage the whole thing, even though we have a cluster, even though we have the applications, even though we have all the technologies, but we need someone to manage it, because we cannot customize this for each and every use case because it's not going to scale, right? So thinking about that, we kind of came up with a kind of a concept, which is the trapezium. Trapezium, the best way to think about trapezium is it's kind of a wrapper. Think about it as a wrapper which actually keeps in control for all these applications you are talking about, right? And it's configurable there, and it can actually handle both badge and stream dataset. So what you do is with the Trapezium, you have a configuration file in the beginning. You create one instance for each of your use case, and you say, here is this what I want in this use case. I want streaming. I want this. This is my pure like some of the functionalities I want in the Trapezium, and let it go. And then that instance will take care of that particular use case, and then you can scale for more and more use cases. That's the whole purpose of why Trapezium was built. Now, again, that same like the conceptual chart I showed earlier, now Trapezium actually lies there. Trapezium is in between. It actually controls the communication between all these application layers, right? And also enables you to see whether you want to use stream, badge, how will be the data flow. Right. So we'll actually go briefly touch on some of the properties of the Trapezium. So think about it. Any use case will actually go through this data access, data validation, data processing, persist, and then the failure, basically handling failure. So think about it. For any use case, these things are actually very common. So are we going to actually build or implement the same code again and again, right? So basically the whole purpose of the Trapezium is kind of to come up with the concept of reducing the code redundancies, right? Basically whatever code we can maximize the use of that code, right? So while doing that, think of it again a cartoon picture where a standard flow looks like this, where data comes from a database, goes through the application, transforms the data into the database again once you have done the transformation, and think of it as a feature extraction, different transformation we do, right? So now this is where the application manager actually stays. What it does is it takes control once the data flows in and decides how it should be stored, how it should be persisted. All these decisions are made by the application manager. And what you'll have to do is create an instance of this application manager with a configuration you would like to adopt for this particular use case. That's what you have to do, right? That's how we scale. Think about it, you can have data coming from HDFS, NFS, or you can have data coming from Kafka, where it's actually a streaming flow, right? So now just what Trapezium does is it actually, from your configuration, it actually reads the configuration, and then it will know that, okay, in this use case we'll have to have Kafka enabled, and then this is how data is going to flow, and it will actually construct the flow structure. One important point I want to figure out here is like handling exceptions. A lot of times when data flows in, like in machine learning, when we think that we are generating features, we are doing some sort of data cleanup, but in practice, when the data flows in, a huge portion of that effort will be to do basic sanity checks on that data. That is done much before the algorithms actually kick in. So those situations are all handled by the application manager itself, and any exception should be caught there before it actually moves forward. And think about it, if you have an organization, if you have a specific type of data, enabling these things, because you know what kind of data flows in, you know what kind of structures you actually expect from the data itself, all those exceptions you can actually configure there and make sure that whenever data flows in for all your use cases, it's being handled. So another important point here is in the run mode, you can actually support both batch and stream workflow, which is kind of a pretty strong capability in that sense. And then basically the job scheduler OZ is actually itself is a framework, and then application manager makes use of all these open source framework and actually takes advantage of that, but then it's actually in control for the whole use case itself. Now this is what I was talking to you, like fault tolerance, because if you have a big data, you'll have to have distributed jobs, but now some of those jobs might fail. For example, I was talking about KNN, right? So basically in KNN, I was maintaining a top K dictionary somewhere, right? Now I have 100 jobs, one of the jobs or a couple of jobs failed somewhere. Who keeps track of that? Because we always need, for example, in time series, always need the latest nearest neighbors, right? Who ensures that when the job was killed, that the job should kick in again, and we'll have to roll up to a situation where we have the latest K nearest neighbor, the time series is being updated. All these things are actually taken care by this particular Trapezium module. And then these are something we already know, right? Because we can actually get to a situation in production where we'll have to handle the storage, we'll have to make decisions where we actually write our output, we'll have to make decisions where we read it from, and in some cases you would like to modify some of the let's say row values or the row expressions, because maybe the data set which came yesterday had some error, and the next day, let's say, a corrected version or some modified version of it came. So there is a need that some of the rows would be inserted and some of the rows would be modified. So it's from the implementation standpoint. So now this is what I was talking few minutes back, that we can actually have a kind of different scenarios where we would like to validate the data, basic sanity checks. There are a lot of existing libraries which can actually help you to do that, but this is actually a wrapper which makes use all these libraries and ensures that every time the data flows in, it goes through the whole pipeline, it goes through Trapezium, and all the sanity checks have been done and all the validations have been completed, right? And then there are two words there on the slide, which is basically the D stream and the RDD. Those are typically application based. So if you want to do a data stream application, that's where the D stream comes in, or else the RDD data structure is more like if you want to read it as a batch and then make a distributed computation on the top of that. So that's something. And then the last few points you can see, like checking number of columns, checking data types, and all this stuff is being handled by the Trapezium. And think of it, in a smaller scale, these are always in control. There is no worries, and no one should be able to even think using Trapezium. But when the data grows and the data is residing in a distributed fashion, that's where this particular Trapezium might be of use. And we have been heavily using Trapezium in Verizon because most of our data sets are actually residing in different distribution centers. So I'll just change a gear a little bit, introduce a new complexity here. Now we have been thinking about we have been talking about a simple security analytics. We have been talking about DDoS, which is the simplest use case. We have been talking about KNN, which is the simplest algorithm. Now I'm bringing in another use case with the same existing setup. I'm saying let's do marketing analytics, right? So here is the data. We have location data. We have clickstream data. It's the simple data set people actually connect to servers. We have hashed MDNs, which are representative of the users visiting different websites and kind of taking some actions maybe. And then these users are actually located at different zip codes throughout the country. And that's actually the overview of the two data set. We actually put this data together and try to find out, can we extract some sort of marketing analytics from that. So these are some of the use cases, typically the geo expansion and basically feeding customers with more value. Try to see how we can actually compare between competitors, how we can actually expand their customer base, and how we can help them actually getting more loyal customers. These are the typical use cases. So here is a typical visualization of that, which was done on the location side. And now you can think this is actually an expansion where we take a seed audience and then we actually expand on the top of that. Now things to note here, in the previous slide we are comparing two groups, right? So basically I have the entire data set. Now I say out of the entire data set I want to choose people who visit bestbuy.com versus people who visit walmart.com and kind of do a comparative study between that. So think of it as a discriminant analysis. If you keep it that way, then it's something we can make use of, right? So the bottom line of this story is, when you do that, what you are doing is you are not loading the entire data now. You are actually selecting part of it, right? So what it means is a subset of the data will be read. Now if you look at the flow is simpler than before, lot of the things you have seen it before, like we have an user who will actually create a, I'm just focusing on this part. So we'll actually create a segment which is an audience segment, and then they will actually go through an audience analyzer. Now the question is, the audience itself is a selection of the small subset of it, right? So the the technology or the kind of the approach we have here is we treat subscribers or users as documents, and we'll actually use the features as their words. So basically, how do you actually parse documents, how do you index documents, and then retrieve the documents? So it's basically information retrieval use case. We treat it that way. So in that case, what you can do is you can retrieve the set of users given the set of features. It's kind of retrieving document analogy is retrieving documents given the set of keywords, something like that. So for this particular purpose, we actually used a Lucene technology. Lucene, actually the Spark technology we use, it's basically columnar based. So we'll have to bring in the Lucene technology, which actually enables us to add this additional complexity on the top of our Trapezium, and Trapezium actually handles this use case as well. So as of at this point, I will stop and see if I can entertain a few questions, and then we can actually discuss further on each of these after the talk, whenever it is. Thank you.